Okay, now we want to look at starting to solve some of these equations, starting with problem number 15. Now, if I compare problems 4 through 14, one thing we realize that they ask for both the general solution and the solution from 0 to 2 pi. Well, the good thing about starting with problem 15, they do not ask for the general solution anymore. So the good thing is all we have to worry about is the solutions between 0 and 2 pi. But now the downside is the equations are becoming a little more complex. So for instance, the first one, problem 15, is 2 cosine squared of theta plus cosine theta equals 0. I think maybe the easiest way to think about these problems is in your mind, especially if you have the same trig function here, like in two different terms, you almost need to think of that as like, what if the trig function instead was like x? In other words, what if you were asked to solve this problem? I think almost all of you could solve this, right? How would you solve this? Well, in this case, you would factor. Matter of fact, you would factor out an x. You'd have 2x plus 1. X times 2x plus 1 equals 0. And then you take these two factors, and the solutions would be when either of these factors are equal 0. So x equals 0 is a solution. And then you set 2x plus 1 equal to 0. And if we solve for x, there are your two solutions. We're going to do the same kind of thing, except instead of x, we just have this trig function, cosine theta. So, just to rewrite it, I'm going to go ahead and now factor out a cosine of theta. So inside the parentheses, 2 cosine theta plus 1. And now I take each of my factors and set it equal to 0. Let's look at this one first. Cosine of theta equals 0. Once again, my solution needs to be theta. So I ask myself, let's go find an angle in radians where if I take the cosine, it equals 0. So once again, in my mind, I'm going to the unit circle. Since it's cosine, I'm thinking of the x-coordinate, and I'm saying, okay, on my unit circle, where is x going to be 0? Two places, right? At the top and the bottom. What are those angles? Pi over 2 and 3 pi over 2. So these are two solutions that come about as a result of the first part of this equation. But now I've got the stuff inside parentheses. I have to set it equal to 0 and solve for it. So I subtract 1 from both sides, divide both sides by 2. When it's all said and done, I now have cosine theta equals -1/2. So now I go back to my unit circle and say, okay, now I'm looking for an angle, or more than one angle, where the cosine is -1/2. I'm looking for some points on my unit circle where the x-coordinate is -1/2. And we've done this before. We know it's got to be on the left-hand side because x has to be negative. And it's actually right there. 2 pi over 3. And down here, 4 pi over 3. So from this, I get the solutions of 2 pi over 3 and 4 pi over 3. So there are actually 4 solutions to this equation. Look at number 18. I'm not actually going to do it. Let me just talk about it. We actually have two different trig functions, but because we have two parentheses multiplied together equals 0. It's almost like they've already factored it. And for this one, I would simply take the first parenthesis, set equal to 0. Now let's think about this. Actually, maybe I'll go and solve this after all, since we haven't done anything with tangent and secant. So far, everything we've done has been sine and cosine. Let's think about tangent. I'm going to convert tangent. For me, it's easiest to convert it to sines and cosines. So really, tangent is sine theta over cosine theta. So now I'm going to go find an angle, basically where sine and cosine are the same, right? Because when I divide them, they have to equal 1. And if I go to my unit circle, where are the sine and the cosine the same? Well, at each of these middle points. Or actually not all of them. This one. Now quadrants 2 and 3, they don't work because the sines, the cosine is negative. Actually, for quadrant 2, it does not work because the cosine is negative, the sine's positive, so the tangent's -1. Cosine 3, both the sine and the cosine are negative, so when you divide them, it's +1. So quadrant 3 works, but quadrant 4 does not work. So basically, quadrant 1, pi over 4, and quadrant 3, that point there is 5 pi over 4. So there's my solutions I get from this first parenthesis. And the second parenthesis, secant theta -1. Well, once again, I don't really like to work with secants. And I know I can change secant to cosine. Let's first solve for secant. Secant theta equals 1, but I know secant theta is 1 over the cosine theta. So I really have is 1 over cosine theta equals 1, which ends up being cosine theta equals 1. So once again, I go to my unit circle and I say, let's go find the angles where the cosine's 1. The cosine is the x-coordinate. Where's the x-coordinate 1? How about right here? What angle is that? That's 0. So in a sense, I have 3 solutions now. I have 0, I have pi over 4, and 5 pi over 4. Let's look at a couple more of these. How about maybe number 20 looks a little complicated. Cosine squared theta minus sine squared theta plus sine theta equals 0. Tricky thing is, I have both sines and cosines, which looks like it could be sort of difficult. What I'd prefer to do is have an equation with either all sines or all cosines. Since I already have 2 sines here, let's see if I can get rid of this cosine squared theta. And then I remember this identity that is probably used the most out of all of them. Sine squared plus cosine squared equals 1. If I solve this thing for cosine squared of theta, it's 1 minus sine squared of theta. Let's substitute that in for this right here. So I end up 1 minus sine squared theta minus sine squared theta I can combine these 2 terms, they're like terms. So I have -2 sine squared theta plus sine theta plus 1 equals 0. And actually I don't like having this negative sign on my first term, so let's multiply both sides by -1. And you know what this is? This is sort of like a trinomial. What's like a quadratic equation with respect to, if you think about it, how would you go about solving an equation like that? You're going to do the same thing, but instead of x, you're going to have a sign. And do I want to take the time to do this? Maybe I can do it quickly. If I think about this, my product is going to be 2. My sum is 1. I guess it's 1 times 1. So I have 2x squared. Oh, I messed up on these signs. Sorry, it's negative and negative. You probably saw that. So this is like this and this. So my sum is negative 1. So I'm going to have 2 and negative 2 and 1. Nope, I keep messing up. Let me slow down. Minus 2 sine squared plus sine squared plus 1. Change the signs. 2 sine squared minus sine minus 1. The product is negative 2. 2 times negative 1. The sum is negative 1. Therefore, my factors are minus 2 and 1. So I can say minus 2x plus x minus 1 equals 0. Factor by grouping. X minus 1 plus x minus 1. So then I have x minus 1 times 2x plus 1 equals 0. But now, for my problem, I actually have sine, so now I say this is really sine theta minus 1 times 2 sine theta plus 1 equals 0. And now, I'll let you finish this. You set sine theta minus 1 equal to 0, solve for theta, and 2 sine theta plus 1, set that equal to 0, solve for theta, and you're good to go. I want to take a quick minute, look at one more that might look a little tricky. Number 21 says tan theta equals 2 sine theta. Once again, two different trig functions. Let's get everything on the left-hand side. Tan theta minus 2 sine theta equals 0. But I know I can rewrite tan theta in terms of sine and cosine. Tan theta is sine theta over cosine theta minus 2 sine theta equals 0. Let's factor out a sine of theta. 1 over cosine theta minus 2 equals 0. So now I have my two factors. So my first problem to solve, sine theta equals 0. When is sine theta 0? What angles? How about 0 and pi? And then I have 1 over cosine theta minus 2 equals 0. 1 over cosine theta equals 2. And if I do some algebra, I eventually end up with cosine theta is 1/2. And I know where's the cosine theta 1/2? It's going to be pi over 3 and 5 pi over 3. So there are your solutions. All right, so now those are the kinds of equations you're solving. If you do them for a little bit, you should maybe get the hang of it and be good to go.